the x tangent hyperbolic of e to the x. There we go. We're done. So just a little product rule and chain rule in there. I almost messed up the chain rule. All right, next thing I'm going to show you I think is just super awesome. Did anyone have questions on this? All right, what I'm about to show you, in my experience teaching, it's almost 100% that nobody has ever seen something done this way. All right, so it's actually pretty exciting whenever I get to it. So we're going to talk real quick about the inverse hyperbolic trig functions, and I'm just showing them on the camera. All right. If we have 6 hyperbolic trig functions now, right? If we have 6 of them, they each have derivatives. We've talked about that. Then, just like in pre-cal, we should have 6 inverse hyperbolic trig functions, shouldn't we? And I'm only going to look at 3 of them. All right, we're only going to look at 3. They don't come up that often, but these 3 do show up sometimes, so we should be familiar with them. And these are the definitions of the inverse hyperbolic trig functions: sine hyperbolic inverse, cosine hyperbolic inverse, tangent hyperbolic inverse. And those are their definitions right there. Pretty ugly. The hyperbolic inverse sine of x is natural log of x plus the square root of x squared plus 1 for all x in the reals. So as long as x is a real number, this is defined. So remember last class when we tried to define the inverse sine function, we had some domain restrictions. Same thing here. We have possibly domain restrictions for these inverse hyperbolic trig functions. For hyperbolic sine, there's no restriction. X can be anything. But for the hyperbolic cosine inverse, we have some restrictions on x. It has to be bigger than 1. Here, x has to be between -1 and 1. All right? So what I'm about to show you right now is example 3 here. I want us to show that the inverse hyperbolic of sine of x is the natural log. So actually show where did that formula come from. And this is cool. Yeah, my definition of cool is different than your definition of cool usually. All right, here we go. We're going to try and show that first one up there. So I'm going to start here with, I'm asking myself, what is sine hyperbolic inverse of x? Okay, that's what I want to know, right? And at the end of the day, I should have natural log x plus square root blah, blah, blah. So here's what I'm going to do, and just see if you follow me or not. I'm going to call this thing y. All right, I'm going to call it y. So I'm trying to find out what y is. Does everyone agree? If I can tell you what y is, and I have y in terms of x. So if I can somehow do something right now and get y equals and then something here that has x's in it, would you be satisfied that I've actually found a formula like that? Maybe? So I'm going to come in here and I'm going to take sine hyperbolic on both sides. Now we did not talk too much at all, in fact, about the cancellation property. Oops, I forgot the hyperbolic right here. That's a sine hyperbolic right there. But I should be able to do the same cancellation property that I had from last class, so long as there aren't any domain problems here. But what does it appear the domain restriction is here? There really is none, right? I mean, so we are okay to play this game taking the inverse, taking the hyperbolic sine on both sides of the equation. So that leaves me with this. Sine hyperbolic y equals x. Now I'm trying to solve for y here, right? Trying to solve for y. And right now, I mean, I can't divide by sin h, right? That would just be, I get like beaten in a chamber in math hell for that. So I have to do something else. I need to release the y from the sine hyperbolic. And so I have no other choice right now but to just go with the definition of what sine hyperbolic of y is. So I'm going to rewrite this using the e's. So the left side of that equation, and Dustin, do you want to give me the left-hand side of this? You probably have it written down somewhere, hopefully. Okay, almost. It's not x, it's what here for us? E to the y minus e to the, right? I'll do 1/2 if that's okay with you. All right, so that's the left-hand side of that equation, right? Equals x. Now, I'm trying to solve for y, right? Trying to get y by itself. All right, I don't like the 1/2. You don't like the 1/2. Multiply both sides by 2. How about we do that? All right, so we don't have a fraction anymore. Now, I always like to give a student an opportunity to blow me away here. And maybe someone actually knows how to solve this for y. But I don't want you to be like, you know, you kind of think you know and you're going to just wander around. I mean, like you either know or you don't here. So if you do, this would be a good time to raise your hand and let me know. Okay, that's a very good instinct to have. Yes and no, we're not there yet. The reason you can't do natural log, because you're thinking natural log is going to kill the e off, right? But there's 2 e's. Well, it's the way you bring natural log in, right? When you do natural log, you have to do it on both sides, don't you? So let's entertain the idea. It's not going to work, but let's entertain the idea. If I do the natural log of the left side, and I'm just going to say a minus b equals natural log of the right side, 2x. See, you cannot kill off these e's because they're separated by subtraction. You cannot distribute natural log to each one because natural log is not a number, so you can't treat it that way. And you cannot split this up into 2 logs because you can't split log into 2 logs unless this is what in here? Multiplication or division. So yes, but it's not going to work because we have 2 e's in there. That's a good instinct. Take the natural log. What do you mean?
Like, if you're essentially taking the natural log of y, then you wouldn't be canceling out the e.
I think that actually plays into the same thing. It's the way that you could bring natural logs in here, but it's the way that you have to do it algebraically. It has to be on both sides. So anything you do here, the natural log has to affect a difference, 2 terms instead of a single term. You're starting to get closer. Say it again.
E to the y equals 2x plus e to the negative y.
All right, I think y'all are starting to get there. It's not addition though.
Can you raise the whole thing to e to the y?
Both sides? Like raise like a power? I think what I'm interpreting is this. That's what you're saying. I don't know if that's what you mean. That's not what you mean? Okay, good. But you're close. All right, so we'd go all day. I just want to make sure that it wasn't like someone automatically that had it. Okay, like, oh yeah, that's obvious to me. You know? All right, so let's check this out. We're going to multiply both sides of the equation by e to the y. Multiply. Because here's what we really have, all right? I'll write it a different way for you. All right, that's what we really have. The e to the negative y really means this. Yes? Okay, now I'm going to multiply both sides of the equation by e to the y. And the idea is that I'm going to clear the fraction that way. But something else great is about to happen. So what happens when I multiply the left side by e to the y and then right side by e to the y? So left side, what do I get? E to the 2y minus 1, right? Because this e to the y and that e to the y cancel out 1 equals 2x e to the y. Okay. So I have some fake money here for whoever wants to get that. Let me just show you. I mean, this is just, it's so cool because it's something you probably have never seen before. All right? So I don't want to waste time with you having to sit there and fumble over it or something. I don't mean that in a rude way. I'm just being honest. Because you could spend the rest of the weekend trying to figure this out. Okay, so I'm bringing everything over to one side. I'm trying to solve for what variable? Y. Okay, what I've done is I've created something that looks like a quadratic. Right? Kind of. It's kind of like I have e to the y squared minus 2x e to the y minus 1 equals 0. Isn't that really what that is? So if I just come in here and I just say, look, just for now, I'm going to replace e to the y with u. I'm going to make a substitution. Everywhere I see e to the y, I'm going to replace it with u. What would this turn into? U squared minus 2xu, right? Minus 1 equals 0. And here's where things can start to get even a little bit crazier. Because this is a quadratic in u, meaning u is the variable, right? But we also have another variable in there, right? X. How do you solve quadratic equations, usually? You try and factor them, right? But if it doesn't factor, what do you use? You complete the square or quadratic formula, right? I'm going to apply the quadratic formula to this. Okay, so let me remind you, because I really want to illustrate this. Here's what everyone knows, right? Everyone knows the quadratic formula looks like this. Right, that's the quadratic formula. If you have a quadratic equation, ax squared plus bx plus c equals 0, then the solutions are x equals what? The number in front of x, right? The number in front of x, change the sign, then plus or minus that number squared, then minus 4ac, and then all over 2a. That's how you do it. What we have here, I'm saying, what is the variable here? U, right? So this is really like a u squared, u, right? So what's in front of u? See, we're used to having a b here, a number, aren't we? But our b is actually negative 2x. It's a variable instead. And a lot of people have never used the quadratic formula to solve for a variable in terms of another variable. It's always been a number here, hasn't it, usually? But I can still apply the formula. So the solutions to this are negative b. What's negative b? Plus 2x, right? The opposite of what I see there. Plus or minus square root. What is b squared? 4x squared. Minus what is 4 times a times c? Because a is 1, right? So 4 times 1 times negative 1. So 4 times 1 times negative 1 all over 2. Questions? U is equal to 2x plus or minus square root of 4x squared plus 4. Can I do anything to that? I can take out a factor of 4 out and then pop that out as a 2 out front, right? Can't I? So take the 4 out of both of those and then pop it out of the root. Oh, we're getting so close now. All right, u is equal to 2x plus or minus, I pop the 2 out. I'm left with, in here, because I pulled a 4 out, x squared plus 1 all over 2. Can I do anything else now?
Reduce
Reduce everything by a factor of 2. Oh, wow. I'm getting close, aren't I? X plus or minus. Now, I have a plus or minus. That one doesn't. And over here I have u. But wait a minute, what was u? E to the y, wasn't it? E to the y is this. And now you can come in with the natural log because you have e to the y by itself. If you do natural log now, it's automatic. It'll spit the y out. But you do natural log here and there. Understand? So, natural log on both sides. Natural log of e to the y equals natural log of x plus or minus square root of x squared plus 1. And the left side is really what? Y. So this is y equals this. Now, that's almost it, right? The plus or minus is a problem. What's that?
We set y equals.
We set what? Y, yeah, in the beginning we said arc sine hyperbolic or hyperbolic inverse sine of x was equal to y. And I said, if I could tell you what y is later, then would you be happy? And so I've told you what y is in terms of x. The plus or minus is still an issue, though, because that says plus, not minus. Let's think about this for a second, all right? Just think about it. This is going to take a little bit more, I guess. You have to step away from it for a second, maybe come back to realize this. What can you not plug into natural logs? You can't plug negative numbers in, right? Natural log of a negative number doesn't exist. So is it possible that x minus this could be negative? Can x minus this be negative? Yes, but let's convince ourselves. Would you agree with me with this statement? X squared plus x is greater than the square root of x squared. Yes? Everyone agree? That left side's bigger than the right side because I'm adding 1 to it, right? Take this, add 1. So if you agree with that, then you agree with this. X. Right? Square root of x squared is x. Absolute value of x, but if we assume that x is positive right now. And now, what? Move this to this side. Look. This inequality says that if you ever have x and you take away the square root of x squared plus 1, it's always what? Less than 0. And that's exactly what we have here in the negative case. X minus the square root of x squared plus 1, we know that that's negative, guaranteed by this logic. So we can never have a negative there, can we? Or it won't work. So I better chunk that. And that's that. And the other two you could get the same way. Isn't that I don't know, maybe it's just me, but isn't that a pretty awesome usage of the quadratic formula? I mean, you don't see that very often. All right, so we have some more derivatives. I don't know where the time goes. I'm not going to show this one because of time. This is a derivative, though. Okay, so look, I'm just going to walk you through it real quick. Oh, I should show my internet class what I'm talking about. I'm just going to walk you through this right here. If I wanted to take the derivative of cosine hyperbolic inverse, then what I would do is I'd come up to the definition of cosine hyperbolic inverse, which is right here, and I would take its derivative, which means I would take the derivative of a natural log. How do you take the derivative of a natural log? 1 over what's in there, then times the derivative of what's in there. If you do that, chain rule on that, you should get this result. And I'll let you do that yourself. But it's just, you're using that formula above, taking derivative using calculus rules. Now, the rest of the derivatives, can be found in the book. I don't remember what page they're on, but they're on your formula sheets too. You should have a section in your formula sheets that has all the trig functions, all their derivatives, all the inverse trig functions and their derivatives, all the hyperbolic trig functions and their derivatives, all the inverse hyperbolic trig functions and their derivatives. That should all be on a sheet in your formulas, all right? So now know where to go to find it. But I want to talk about a very nice example. This is called a catenary. So if I were to take a look at the hyperbolic cosine function, we said it kind of looked like a parabola, right? Didn't we? Kind of looked like a parabola. Anybody know what a catenary is? I mean, I kind of give it away up there already. Okay, so if you take a wire, I need a volunteer. Let's see. Robert, thank you for volunteering. Here you go. If I take a wire and I hang a wire, let's just hang it like this, just like that. If we hang a wire, what is this shape? It looks like a parabola, right? But it's not. There's no quadratic function that you could lay right on top of this. There is, however, a function that does lay on it, and it's a catenary, and it's a cosine hyperbolic function. So what I want you to do, Robert, is put your end right there. I'm going to put my end right here, and I guarantee you it's going to be right on top of that blue thing. So there we go. If I tighten this up, let's see. See that? That's the only way it could possibly happen. So what happens if we move yours over a little bit? Then you say, wait, that's not it. So hang tight. Or Ivana, you can hold the other side if you want. So look, I'm going to change it. So what I'm going to do is I'm going to adjust the value of A. And that's going to adjust the catenary. So see if y'all can make that one happen. See? So every hanging wire, no matter how you do it, can be modeled with a hyperbolic cosine function. So they're very important because you can let it go. Thank you. That's all I needed. Is that somewhat convincing that that function works for the hanging wire? All right, hopefully you're convinced. So what are the things that we would want that for? Why would we want to know the graph, the function that gives you a hanging wire? Just because that's fun to know, or what?
Do you ever have to hang wire?
Yeah, what if you have to hang wire?
Maybe building suspension bridges.
Yeah, if you're building a bridge. You know it's a cosine hyperbolic function. So here's a specific example, all right? Let's say that we have a catenary that looks like this. We have a pole, here's the ground, another pole here, and we're hanging a wire between them, like this. Okay? There's our catenary right there. And we can show that if you look at the lowest point on the catenary here as being the middle, and you measure out to the first pole, let's say it's 7 feet to that first pole, that we have modeled that red catenary to this function. Y equals 20 cosine hyperbolic of x over 20 minus 15. So the minus 15 on the end, I didn't show you what that is. That just moves your catenary up and down. Okay, so if you want to put it on a taller pole or a lower pole, okay, so that's all that does. Okay, so this is the model of that red catenary. Got it? Here's the question. I want you to find the angle between the red catenary and the pole. The angle. Because look, there's forces involved here, right? There are forces. The mass of the wire is, gravity, and that's pulling the poles in, and the mount that I have that's holding that red wire there has to be strong enough to hold that force, right? I mean, got to build it, engineer it properly. And so I need to know the angle that is going to be pulling on that harness, that connection. I need to know what that angle is. Because we all hopefully know that it's different if you pull on something straight as opposed to pulling out on an angle, the forces are completely different. So knowing that angle is important. How are we going to do it? Anyone have any ideas? I won't call on anyone. So the question I'll put up here, find the angle between wire and pole. You might be asking yourself some questions like, what does he mean by the angle between wire and pole? Like, where are we talking about? What angle? Are you thinking that? Like, okay, you're on to it, Ron, right? Ron, am I right? See, I learned at least your name for today, and I'll forget it. Okay, so Ron is suggesting that we find the what? The derivative of the wire. The derivative represents the what? That's other way. First, the derivative from Cal 1 represents the slope of the tangent line, doesn't it? So Ron's suggesting that we find the derivative, which would represent the slope of this line, and you said as close as we possibly can to that point, right? So you want to go as close as we possibly can? Okay. Can we actually go to that point? Can you find the derivative of a function at a point? Sure. So if we actually pick that point right there, and we find the slope of the tangent line, that will form an angle, theta, won't it? That's exactly the way we want to look at it. So that means you're going to have to first figure out what the slope of that blue line is, which is the derivative of that function at what point? At 7. So let's take the derivative of that first. What is the derivative of that? All right, what about the 20 in front? Just leave it, right? What's the derivative of cosine hyperbolic of something? Sine hyperbolic, right? Of that something? Am I done? Derivative what's inside? What's the derivative of 1/20th x? Because that's what x over 20 means, right? What's the derivative of 1/20th x? 1/20th. So we need to tack that onto the end. And then we're done with chain rule on this. Derivative of negative 15? 0. So this is it, right? And I think our 20 and 1/20th cancel. So all we get is the hyperbolic sine of x over 20. Are you all with me? Yes? Now, if I could tell you now the derivative at 7, that would give me the slope of that blue line. So the derivative at the value 7 is equal to sine hyperbolic of 7 over 20. Now, your calculators do a lot of times have the hyperbolic trig functions on them. But let me remind you of another way you could compute this. It would still require your calculator. 1/2 e to the 7/20ths minus e to the negative 7/20ths. Right? So what I'm doing is, this is hyperbolic sine of x. And so we know that that is 1/2 e to the x minus e to the negative x, replacing x with 7/20ths. And what I would like for you to do is on your own, you don't have to do it now, make sure that you can plug this into your calculator and get the correct answer out of this. You should get about 0.35712. And I rounded that last digit. And I'm going to go out 5 decimal places here. 4 or 5 decimal places. Now, am I done? What does this quantity represent? The slope of that tangent line. What is the question asking? The angle between the wire and the pole. Is that slope the angle? No, the slope's not the angle. How are you going to get that to an angle? Yes?
When you extend the line of the slope, is it going to meet at the 0?
Nope, doesn't have to. What is slope by definition? Rise over run, right? So let me help you with this. We want to know what theta is. Do you agree? All right. And what we know is this slope, rise over run. So if I take that triangle right there, and I draw that triangle a little bigger so you can see it, and here's the pole, and we're trying to figure out what theta is. If I tell you I'm going to stop this triangle somewhere, right? It goes down, I could keep going, right, with it. I'm going to stop it arbitrarily when this side is 1. Then what is this side? 0.35712. Because you just told me that slope is rise over run, right? And if I write this way, rise is this, run is this, rise over run is this, right? I'm just cleverly using 1 here, and that forces this side to be this. Understand? Can you give me theta now? What's the trig function that connects theta to those sides? Tangent. I know that tangent theta right now is what? Careful with where that theta is. 1 over 0.35712. Right? Tangent is opposite over adjacent. So I have to turn my head opposite over adjacent. If theta was down here, it'd be different, right? Then I would do that over that. Okay, so someone tell me what I can do now, because I'm trying to solve for theta. Arctan on both sides, good. So if I take inverse tangent on the left side, I get theta. What I do to the left, I have to do to the right. So who's going to give me the answer off their calculator? And make sure you know what mode you're in, because I want the answer in degrees if possible. So make sure you're in degree mode.
70.35.
Yep, 70.35 degrees. Approximately. We're rounding here, but that's good enough. So the angle at that point is 70.35 degrees. Pretty good. Well, I thought we'd get to 4.7 today, but we didn't. We have a couple more minutes. I'm just going to put a couple of problems up here for you to try until time runs out. All right? These are derivative problems. Just practice taking some derivatives. Your homework. I've changed the homework assignment a little bit, so if you printed the notes off the web, what's highlighted in yellow is additional. 48 I planned on doing in class today, so what I'm going to do is just say that 48 is going to be a bonus question, all right, to be turned in at the beginning of class next time. So 48 is a bonus question to be turned in at the beginning of class. And because I didn't do 48, 49 relies on 48, so you can kind of scrap this, 49, all right? Everyone understand? 48 is a bonus? Mm-hmm. Okay. Both of these, find the derivatives. These are not designed to be like nasty problems. It's just basic differentiation. So if you can do those, you're free to go after you're done or if time expires here. Anybody need to sign in? Anyone? Yes? Initial. What's that?
I didn't realize homework was mandatory.
That you didn't have to turn it in? Yeah. I can't imagine trying to grade all of your homework. I think that would be kind of hard. Right? But on the other hand, students who don't usually do their homework usually aren't here to talk about exam 2. You know, so. All right, y'all go ahead. I know y'all want to get out of here, but see if you can at least get these two. I'll put the formulas up here for you. There. Those are the only derivatives you need for this. Don't turn these into e's, okay? Go off of that. So derivative of tangent hyperbolic is secant hyperbolic squared, and just go straight with that. A lot of the E stuff I did today was just to get you used to that sort of math. I mean, that's, as you progress through the engineering fields, I mean, all that stuff you saw, I mean, that's just natural, comes with the territory type of stuff.
So you don't want us to put the E all the way.
Unless it says, like, prove this identity, then you have to do that. Other than that, it's use the formulas. That's what they're there for. All right, I'm going to shut this camera off.